Thank you very much. My name is Gopal. I'm a fifth-year PhD student at Brown University. I work with Brenda Rubenstein, and I'd like to discuss, we've seen some excellent talks on, more solid-state facing electronic structure theory. What I'd like to do now is take you to the world of atomistic reaction engineering and see if we might be able to use some tools that we've seen over the past few days to address some questions in that field. Specifically, I'm going to use the surrogate Hessian line search method that Jaron described yesterday to identify the minimum energy pathways that exist between equilibrium states when you have a stochastic potential energy surface of the kind that you would have if you do diffusion Monte Carlo calculations. So before I begin, I want to acknowledge support from the DOE and the Air Force Office of Scientific Research and the generous support of Brown Department of Chemistry and the Center for Computation and Visualization at Brown, which is the home of the Oscar supercomputing cluster, which is where I performed all these calculations. Great people, not enough CPUs. Okay, so let's begin. So I want to motivate this by plugging some work that I'd done a couple of years ago. So we know often that when dealing with reactive potential energy surfaces, we need sub-millihartree resolution of the energies in both precision and accuracy. So a very popular example of this is the carbon monoxide on platinum 111 puzzle. So this was identified 20 years ago, which says that a variety of DFT-GGA functionals actually predict the incorrect stability of the different absorption sites on the platinum 111 surface. And so theory predicts that the threefold is more stable than the twofold, which is more stable than onefold, but experiment predicts exactly the reverse. And so we thought of attacking this problem with diffusion Monte Carlo, and what we found is that it unambiguously recovers the correct site reference, where lower is better, lower is more stable, and so we get this correct site order immediately. So this is encouraging, but at the time, for the equilibrium states, we had to optimize the geometries using DFT, and then just convert that to QMC or a compatible format, and then run DMC calculation to get these energies, which is well and good for the equilibrium states. But what if you are interested in the non-equilibrium path that a molecule has to take when diffusing from one absorption site to another, for example? And so the best option we had for that at the time was to run a DFT nudged elastic band calculation, which we'll get to in a second. And then for each point along that path, you just do another diffusion Monte Carlo calculation. And so even though this gives us some interesting results, we don't know whether or not the path is accurate because we can only do it at the DFT level. And if you look closely, the DFT path that is revealed with the DFT NAB calculation is this weird L-shaped curve when going from the top to the hollow site, as opposed to just sliding down directly along a linear path. So this is quite strange, and we didn't know at the time whether this was accurate or not. So before I go any further, I just want to note that equilibrium geometry optimization for DMC has been solved, as we saw yesterday. And just to quickly summarize that method, you first take your system, convert it to some reduced structural parameterization as far as you can, so that you have fewer, like a smaller space to optimize within. You compute local Hessian using a surrogate theory, usually DFT, compute the eigenvectors, and then perform a line search along those eigenvectors. And you can also tune the precision to which you identify these structural parameters by looking at the maximum tolerated point-wise noise that you can have at each point along the DMC line search grid that you create. And it turns out that it's actually fairly simple to generalize this to saddle points as well, because if you start at a good starting guess for a saddle point, the only change you have to make is that one of the eigenvalues of the surrogate Hessian that you compute will be negative. And so instead of minimizing the energy along that eigenvector, you just maximize it. So this is a solved problem, and we will be looking at some results specifically about that in a second. But now the question is, how do you go about identifying minimum energy pathways between equilibrium states completely using DMC? And when I say force-free approach, I mean you don't use forces from DMC at all. Instead, you just rely on the Hessian that you obtain from the surrogate theory. So, I mean, we've seen some great work on force calculations for, just like based on DMC, but you may not be able to do that for every system. Okay, so let's start by just defining what a minimum energy pathway is. So in the chemistry community, this was defined by Fukui in 1970 as the intrinsic reaction coordinate. And so it's just a pathway and configuration space that connects two equilibrium states. It passes through a saddle point, which we assume to be first order for simplicity, and it runs along a groove if you look at the PES. And what I mean by groove is that if you look orthogonal to the path, it lies at an energy minimum. And you'll notice that the definition of the MEP itself contains a reference to the pathway itself. And so we know that in the physical sciences, whenever you see a self-referencing definition, it usually means that you can use a self-consistent scheme to solve it, which is actually what you see with the second Hohenberg-Kohn theorem and DFT. It's self-referencing definition. So how do we typically solve this with deterministic, ab initio or atomistic methods? You use nudge elastic band. You use other methods too, but I'll summarize this because it's pretty popular in the catalysis community. So let's say you have two equilibrium states, which are these points in the yellow region of the energy contour. And then you have like some interpolated path, which is the green points, which is typically a bad approximation to the MEP. What you do is then you compute tangents along the path at each of these points using some formula that I won't get into, and then you calculate the forces on each of the atoms at each of these configurations. You then resolve the forces along and orthogonal to the path, and then set the component along the path to 0. So you're only left with a force that's orthogonal to the path, and then you move in small discrete iterations toward like a force converged set of states. And so that is the pink dots that you see. It's slightly, a better approximation to the MEP than you would get just by a linear interpolation, for example. And then there's other, additions. You can add like spring forces to make sure that there's an even spacing of states along the path, but we won't get into that. So how do we now translate this to the language of a stochastic PES that we would obtain from DMC? It turns out that it's quite intuitive. So let's say you start with a path that you got from nudge elastic band, which is the pink points. Again, you compute the tangents as you would for NEB, but then you construct a subspace of the overall structural parameter space that's orthogonal to that tangent. And so for each point along the path, you're constructing a subspace that is, that has one fewer dimension than the overall space. And so within this subspace, you have to define an auxiliary mapping that goes from the structural parameters to this subspace. And then what you do is you just proceed as you would with a regular surrogate Hessian method, which is you compute a finite difference Hessian locally around each structure, which needs to have those directions and that origin well defined. And then once you have the surrogate Hessian, you can just do a line search as you would with like an equilibrium or a saddle point. So the good thing about this is that we have basically found a way to do this without relying on quantum Monte Carlo energy gradients. We're just making the approximation that the DFT Hessian is accurate enough for our purposes. And so ultimately you would be left with points that are very close to the true minimum energy pathway that we could obtain with a couple clusters. Okay, so let's see this in action. We're doing this for two simple systems. I'm just gonna see if I'm good on time. Okay, first system is just inverting the ammonia molecule. It's very simple. Parameterize it with two, numbers, which is just the average NH bond length and the bond angle that's made by the average NH bond with the negative x-axis. And so the reason you ground it in a Cartesian reference frame like this is because you want to distinguish between the initial and final states, which are actually both C3b symmetry and they're equivalent. So by doing this, you break that symmetry so that you can identify two equilibria and they're connected by first order sum. So okay, so this nicely summarizes all the results that I want to show you. So you start with an interpolated path, which is the yellow dashed line. And then if you do DFT NEB, you're left with the yellow solid line that you see over here. Now, if you compute surrogate Hessians along each of these intermediate states and then displace the initial guess before doing the line search, if you do the line search using the same DFT theory, you get a path that almost exactly coincides with the DFT-NEB path, which is quite an encouraging result. So then if you take those same Hessians, but then run a DMC line search, you get the turquoise path that you see over there. And if you compare that with a couple cluster singles, doubles, NEB path, it turns out that CCSD is actually closer to the DMC pathway than it is to either of the DFT pathways, which is very nice. And so what you see in the background is just a couple cluster heat map that you've generated, like with a grid of points. And so there's like 2 minima, and then the system just traveled along the MEP through this sort of saddle point. And so we're dealing with really fine structural and energetic resolution. And so it's great that, we can get that level of precision. So here's what the energy landscape looks like. Again, it's minuscule. It's like less than 10 millielectron volts from the lowest to the highest point. But we can, we can get great energy resolution, comparing DMC with a couple cluster. And so we also do like a Gaussian process fit to the DMC points, just so that you get like a continuous version of what the energy barrier looks like. And DFT using subspace optimization surrogate Hessian and NEB overlap exactly in terms of the energies. And so that is also great, which speaks to the fact that this is more an energy optimization than anything else. It's not optimizing the path, it's optimizing the energies, and you can get slightly different paths that actually correspond to the same sort of one-dimensional manifold that connects two equilibrium states. So here's another system. I won't dwell too much on this, but it's just like a simple SN2 reaction, but in addition to the bond length and the bond angle, we also have 2 additional bond lengths, which is, the 2 carbon fluorine bonds. So I'll give you a minute to just take a look at this, take it in, and then we'll look at the results. Okay, I hope that was enough. All right, so we won't look at this, but to summarize, the trend in structural parameters as you progress through the reaction is accurately captured by this subspace optimization procedure, whether you're using DFT or DMC. And so, the trend is generally the same. They do identify moderately different points along the path, but we won't look at this too much. Let's look at the energy barriers again. What we see in this case is that the difference in potential energy between the minimum and the maximum is underestimated by the DFT methods by up to 15 millielectron volts, and this is just a small molecule. So if you were to do this for an adsorbate diffusing on a surface or any other type of surface reaction, this could become even more pronounced. And it's important to get these accurately because these determine the reaction rates that go downstream into computing, like whatever industrial process you're trying to check the feasibility of. So this is very interesting. Okay, so don't look at the table. To summarize, equilibrium and transition state geometries using the standard approach are predicted very nicely by DMC, especially along the parameters to which the energy is very sensitive. And so, you get bond lengths that are between DFT and CCSD in almost all cases. So this is great. Another question is, let's say you wanted to do thermodynamics and kinetics using these structures. How would you go about doing that given what you have at the DMC level and using the surrogate PES? Problem with DMC is that you have a stochastic PES, and so it makes it difficult to compute a finite difference Hessian in order to evaluate the vibrational energies which go into enthalpies and free energies. And so how do we go about doing that? Okay, so the way you would do this in a standard thermochemistry package is that you just break down the enthalpy and the entropy into transitional rotational components, and evaluate them all separately according to some rule. Yeah, that's how you would do it. How do you do this when you have a stochastic PES? There's a very subtle idea at play here, which is actually what drives the surrogate Hessian method, which is that if you look at a sufficiently local region of configuration space around a critical point, the critical point has a mathematical definition that exists independently of the theory that was used to arrive at that point and of the exact structural coordinates that correspond to that point. So what this allows us to do is to take 2 different minima that were obtained using 2 different theories and collect different contributions from both of them. So using the DFT minimum, we can calculate all the vibrational energies by just looking at the local finite difference Hessian around the DFT minimum, for example, and then around the DMC minimum, you would just collect the potential energy. So that's how you compute the enthalpy. For the entropy, it's a little more complicated because you have to know how the errors in the structural parameters propagate into the rotational entropy. So for that, what we do is that we just sample a number of structures around the stochastically determined DMC structural minimum, and then see how that affects the errors in the rotational entropy. And then for all the vibrational contributions, you just look around the DFT minimum or saddle point, and that's how you sort of combine all of these contributions to get like a hybrid DFT QMC, so entropy and enthalpy. And so again, we haven't decided how best to plot this, so I just have another table for you. Using these free energy differences, you can then compute equilibrium and rate constants using the free energy differences between two equilibrium states, or the equilibrium and the saddle point. So in the ammonia case, the free energy differences are very hard to resolve because they're all very close by, but we can still see that the hybrid approach improves upon DFT very, very slightly. And this does translate into a better estimation of the forward reaction rate constant. This is particularly pronounced in the SN2 case because, because the potential energy difference between equilibrium and saddle is very low in DFT, but it's very high in QMC and CCSD. And so we can get great free energy differences using this hybrid approach that almost exactly match with coupled cluster. And because, you have to do exponentiation and the errors propagate, they get magnified when you compute the rate constants. This translates into significant differences in forward rate constant between DFT and the other approaches. And, the equilibrium free energy differences in equilibrium constants are trivial because they're both identical. But as far as statistical error allows, we see that the hybrid approach actually predicts it correctly well within the first standard deviation, which is great. Okay, and so that was it actually. We have seen that we can generalize the surrogate Hessian approach to identify MEPs for stochastic potential energy surfaces, and it performs competitively with nudged elastic band at identifying paths with post-DFT accuracy. And it fully accounts for the fact that you will have statistical errors in the structure. And then just like borrowing this hybrid approach, borrowing the vibrational energies from DMC, you can then get thermodynamic and kinetic quantities downstream. So that was my talk. So thank you very much to Jaren and Yuha, who have been helping with this project with some great insights and practical advice. Brenda Rubenstein is my advisor. Like I said, she's a brilliant interdisciplinary thinker, and Noah Welpley is an undergrad who's been helping with this. Thank you to the organizers, and thanks to the team for answering my questions over the years. You've been very helpful, and I'll take any questions.
Thanks so much, Gopal. Very interesting questions.
I'm not sure they know about the ASC implementation of GP mean, searching the local minima and NAP's transition states.
Oh, I looked at it, but I didn't go to
okay, so it'll be very interesting to couple your method with this method. So for your method, do you always need to parameterize the transition state along the special coordinates?
There's nothing in the formalism that says you have to do the parameterization. You could do it in full Cartesian space if you wanted to. It would just be many more optimization problems to solve. Yeah.
So the GP mean actually what it does, it's already using Gaussian process to minimize number of steps.
Oh, interesting.
Have the whole PES structure.
Oh,
but it's all done at DFT levels. It's very interesting. You can have the cubes and of that.
Oh, okay. So you automate the selection of intermediate states. Okay.
At the back.
Yes.
Just how automated, like in most of the electronic structure programs, if you want to get them out, you just you put it on a vibrational calculation, and it'll just give you the thermal contribution.
That's a very good question. I didn't get into that.
Like ONR runs millions of molecules. Can we just do that now?
Right. Okay. So for both the systems that I showed you just now, it was exactly the same scripts. You had to change almost nothing. You would, presumably have to change very little if you were working with like a slab and, many atoms or like a solid state system. So it is quite generalizable. So, yeah.
And then just one thing about, on the pathway, like, I understand the transition state is going to be, like, you are at a stationary point, but where does how do you get a stationary point for if you're on the slope of the potential energy surface?
Right, so you restrict yourself to only looking at the region orthogonal to the path.
Okay,
So you don't move along the
Yeah.
path at all.
okay, thank you.
Question at the front here?
Good talk. I have a question because, two questions actually. I have an interest in diffusivity of defects in solids. So, do you think this method would be applied to solids,
100%.
for example, to study diffusivity?
You could, yeah, absolutely.
Other question is, I don't know if I missed if you mentioned that, but how can you compare your results using this method with the previous one when you just get the structure from DFT and, for example, for the saddle points, you just calculate the GMC energies
Right.
with respect to this method that you presented today? What's the biggest difference and
Oh,
why do you think this is the best,
That's-
better than that?
oh, you mean compared to the surrogate Hessian approach just for computing saddle points?
The Hessian approach
Okay.
compared to the previous one that you just get the structure and calculate the GMC energies.
Oh, I see. Okay, okay. I mean, okay.
How different it is and why is it better?
So, okay, so because if you're borrowing a structure from DFT, you're looking at essentially the incorrect region of the PES, of the DMC PES, right? But if you get the correct structure, you know that you are more accurately looking at the DMC minimum, for example, or the saddle point. And so in DFT NEB, the way you identify the saddle point is with climbing image natural elastic band. So there is an analog here as well. You could do that.